I introduce Stella in the meantime?
1 second, she hasn't shared. Did you start?
All right, while she's sharing, I'll just start and introduce. So we're really fortunate to have Stella Yu visiting to give the seminar today. Stella is a professor at the University of Michigan in the Electrical Engineering Computer Science Department. And before that, she was at UC Berkeley as the director of the Vision Group in ICSE. She did her PhD at CMU, and she's a real pioneer in unsupervised learning for computer vision mostly, but also a lot of other general purpose machine learning applications in robotics and computational imaging. And so today she's going to talk about grounded visual learning, a way of trying to learn from data without imposing any real constraints. So we're really excited to have you here, Stella. Thanks so much, and happy to see what you have to tell us.
Okay. Thank you so much for inviting me. It's really an honor. There's so many people's work I admire at UT Austin. I had a wonderful visit so far with all the one-on-one meetings, and I learned so much from the exciting work at UT Austin. So I'm a computer vision researcher, and I study the question. Oh, what happened? Okay, I studied the question, what does it mean by seeing? What's the purpose of seeing? If we'll look around the scene, take in a few glimpses. Usually people think about this as an inverse problem. You want to get sense of the 3D world existing outside the person, the embodied agent. And when you take that view, people think about treat vision as a multifaceted inverse learning problem, going from partial observations you capture from videos, images. If you want to do recognition, you want to put the semantics. If you want to do segmentation, you want to outline the object of interest. If you want to do reconstruction, you want to do 3D reconstruction. And this view has led to, this philosophy has led to, it's taken to a large scale. For example, SAM, foundation model for image segmentation. And it was introduced in 2023, and it's a model trained on 1 billion masks and 11 million images. It takes an image, you have a prompt, let's say point prompt, and the details don't matter, and you can fit it with a lot of data, and you give 3 possible answers. Obviously, segmentation is intrinsically ambiguous. You don't know what is the unit of thing you are pointing. Could be the whole scissor, part of the scissor, or just a component of it. And you can see that the kind of data it's trained on. There's a painstaking job from humans annotating the outlines. So these are more granularities. And for recognition, you have CLIP. That's a foundation model for image text association. From such data, one example of this is if you want to grasp the concept of French cat, you search all these examples that people label as French cat, and then you ask model to do it. And this is giving this model, poor model, this is flashcards. Here's an example of French cat. Here's another. And the poor model, is really miserable, and the whole learning process can be thought of as a drilling process. You're going through all the drills, try to learn a representation that captures this French cat. And so you can see that in computer vision community exemplified by this Omni data project, it's treating everything the downstream tasks are interested in. You can have low-level image reconstruction, or you can mid-level key points, normals, so on and so forth. At high level, of course, you have recognition, detection, segmentation. Each of them is a task of interest. If you can build a 3D model, you know everything. So you can learn it, fit into a model with input and desired outputs. That leads to undifferentiated supervised learning. With the current capacity of the model, you can learn anything, really, if you formulate the input and output. My problem with this line approach is that there are 3 folds. One is that there's too much text. Can we see without text? Secondly, too much supervision, okay? And then thirdly, it's undifferentiated. You don't really especially with multimodal learning, right? People don't really care about the nature of the data anymore, right? All tokenization and so on and so forth. So my view to this, I take the developmental perspective. The babies don't get exposed to all kinds of data at the birth time. Only a few items on this musical mobile, but it study each item to his or her heart's content, right? And I think that's this learning process is a modeling process. It's trying to relate what the baby sees at this moment to next moment when the head moves, when the eyes moves, and all these. How are these partial observations relate to each other? And through that, it makes sense of the 3D world outside. So I liken the model we're going to build is the blank slate model. It's like a baby. And the research has the steady eyes. How do we train a model going from clueless eyes to steady eyes? Okay. And usually the main approach is going for this drilling. You think about what's best for the baby. You isolate these tasks and train a model for this. And this leads to fragmentation. Everything is piecemeal analysis and everything is what you want. It's very task-driven and downstream application-driven. On the other hand, I want this modeling process. All you have is multi-sensory data. You want to make sense of the sensory data, and in the process, you understand the 3D world. So in my research, I always ask my this question: what can we learn from nothing but data? Okay, here there's some videos. When you look at these videos, for example, there's a mother carrying a baby walking on beach. Each clip, you don't spend a lot of time looking at this because to you, you already have concepts of, babies, mothers, beach, so on and so forth. That's why you can grasp it so quickly. But if you have to model like a baby, you have to think like a baby. The babies don't have the preconception of objects yet. What can you learn? How can you learn? Okay, the first work I want to talk about is unsupervised learning of generic objectness. Given unlabeled videos, I don't have anything, no labels, no even like earlier edge detection, optic flow, none of that. I want to be able to put a hotspot on every frame in the video. In computer vision, people call this unsupervised video object segmentation. The challenge is that, for videos like this, you don't need to understand a lot, just do sort of a color appearance segmentation, you will get it. You'll understand the elephants will pop out. On the other end, if I freeze the video, you won't be able to see the moving fish, okay? And reality is that sometimes appearance dominates and sometimes motion dominates, and reality is somewhere in between. Even when these animals, they have different head, neck, legs, and each animal is moving at different speed, you see the whole group motion. So this is a traditional problem. Usually people treated this as a sequence of images. You derive audio flow information. You treat this cue integration problem. Not only you have appearance cues, you also have flow cues. And then you can do a better job at segmenting the objects. We turn the problem the other way. You ask me for a set of segmentation masks. I'm going to ask myself another set of problems. What is the flow for each segment? I don't have answers for that. It's unlabeled, right? I'm going, instead of providing one set of unknowns, I volunteer another set of unknowns, but these are tightly coupled together, actually makes the problem easier. Very basics, what is flow? Flow is here, it simply means displacement across frames in the 2D image. So this schematic, the horse moved, and then you look at, compared to previous frame, how the corresponding pixels move. And then the textbook definition of flow is to look at the corresponding points and figure out the delta x for each point, so their intensity is match. And here it's specific to image pair, and for each pixel you solve this independently. That's the very basic version of brightness constancy for optical flow. We use the exact same idea, but we make few tweaks. First of all, we are using a model to capture that flow calculation, it's statistical, it's summarized over all the training pairs. And we also assume that the flow is the same per segment. The only problem is that we don't have segmentation. The segmentation is unknown. The idea is simple. We assume the world is made of few pieces. Each piece moves at some constant speed. And if I have this assumption, I know the segmentation, I know how segment moves, I should be able to construct next frame and match. So how do we do this? We are going to concurrently learn segmentation and flow. Given an image, I have segmentation network and it outputs segmentation, but I don't have ground truth for it. And I take two images, I will have flow estimation. I don't have the ground truth for flow estimation. But if I have these two pieces of information, I should be able to just do copy and paste. This segment, you move this much, I move it, I compose estimate of the next frame. I do have the next frame, so I can compare, okay? So it's a structured prediction problem. The thing I love about deep learning is that you really model at a very different stage. I feel like I'm director, right? I just have assigned each actor what you need to do, but how to do it is your job. You have years of training or whatever, but the actors have to interact with each other, deliver the things I want, okay? That's what it is. Even though I don't have ground truth for either segmentation or flow estimation, they have to be in sync with each other. And this loss, the reconstruction loss, is minimum only when both are correct. You cannot have correct segmentation, the wrong flow, or the correct flow, the wrong segmentation. Okay, for those who are into details, if you have image, you have pixel-wise softmax, you have soft segmentation. Take two images, you have the feature and you have correlation. And from that, you try to predict one 2D flow based on the segmentation mask. You want to predict one segment 2D flow. And then you broadcast to every pixel and you can construct a per pixel flow. And then you use that to copy and paste it. There's no decoder involved, very simple. And then you close the loop with this loss comparing to the actual frame. And this, what's interesting is we train only on YouTube VOS. It's had 4,000 videos, on average 5 seconds long, and 94 categories. We don't use any of the labels, but just to give you a sense of the variety. And so then once it's trained, remember the segmentation only requires one image. So we can apply the segmentation model to single image. And then we look at the results. So let's say we look for 5 segments. So the 5 channels were born equal. I don't specialize any channel for any purpose. So you can see the first frame seems to capture the object in the center, and the rest is the fragmentation of the background. Another image, you see the same thing, capture the human, and the rest is again the fragmentation, so on and so forth. Now this is our aha moments in scientific discovery. Even though the 5 channels are born equal, this one channel seemed to capture the objectness. I was expecting some of the channel likes horses, some channels like, desks, none of that. It's actually all the objects is concentrated in one channel. And so objectness emerges in a particular channel, even though we don't design for it, okay? So we wonder why all the objects concentrate in one channel. So we did some statistics. Eventually, you can see that the channel 0, the objectness channel, can be characterized by very sharp segmentation, characterized the entropy of the values, or it's characterized by the reconstruction error. It has the largest reconstruction error among all the channels. And then the last statistics about the channel 0 tend to be right at the center. So there's something about people call the photographer's bias. It's not like I have the camcorder in my hand, I walk around aimlessly. It's a photographer, try to keep track. But if you look into detailed clips, there's like a static camera looking at a chicken coop. So there's not necessarily always have object in set. Okay, but what this allows us to do is that I can figure out what is this channel, objectness channel, without using any labels. I can just look at a reconstruction error, for example. And why is that? The thing is, if there's a moving object, doesn't matter it's caused by the movement of the object or by the camera. If there's a separation caused by the movement, then if you make mistake in the segmentation, you will have very big reconstruction error, right? But if it's in the background, then if some grass somewhere, if you belong to the different neighboring segment, the reconstruction actually is small. Okay, and so in a way, we distill the movement information into single image-based appearance segmentation. So on 3 different data sets, very different characteristics. The last one, so much camera shaking, we can still get the moving objects. This is all 0 shot. Our method doesn't require any labels. At the inference time, we can continue fine-tuning on the specific video. That's the result you are seeing. Okay, so because we can work on the model, segmentation model can be applied to single image, we work on this benchmark for saliency, DUTS data set. The first 2 columns is, oh, that's not surprising. All these things are like cars, animals, people. These are moving objects. But look at the last frame. We can even pick out a statue, a plate, something on the facade, So that's to me, it's very interesting when we get these results, because we were not looking for objectness. It's really a kind of discovery. It's a aha moment for us. And I was shaken for someone who has worked on segmentation for so long, who are used to like edge detection, contour completion, then figure ground. And this figure ground segmentation can be learned without any preconception of edges, optical flows, saliency. The only thing we assume is instantaneous visual constancy between one frame to the next. The world hasn't changed drastically. Okay, that's all we assumed. Okay, so that's the first work. Any questions so far? Yes.
So is there anything, so objectness is sort of coherence of objects as they're moving through the environment. I think that redundancy between flow and segmentation is nice. There's another further sort of possible decomposition that objects, some things about objects are static and some things change over time. Do you
Trees.
explain that at all?
Trees. Initially, we have used trees example. I said, why trees? Trees are more static, but think about you drive through and the trees, they themselves are static, but you are moving. So we don't differentiate. We only look at the 2D flows. It doesn't matter it's camera motion or object motion, but there's a separation due to the motion, the optical flow differences. That's what matters. People always think the objects, babies discover objectness, motion is a critical cue, but it's only like conjecture. No one actually has built a model to demonstrate that. I like this, the structural decomposition where you are trying to reconstruct the image. And through that, we impose 2 bottlenecks. One is we don't look for 20 segments. We only look for 5. We squeeze it really hard. And we assume each second constraints is that we assume each segment is doing piecewise constant motion. So by squeezing that, we actually get a very nice objectness. Okay. Yeah.
You talked about photographer's bias.
Yeah.
What if the data you learned over wasn't captured by a human, but captured by a robot?
Yes. Beautiful
Just
question.
sort of
Beautiful
wanders.
question.
Does that impact the?
I think data, yes, data matters. So related thing will be what we are working on is if I have empty rooms, I just have a camcorder, look around, can I actually figure out the spatial layout of the room? I want to segment not by objects. I want to figure out, this is wall, there's another walls of different or another wall of different orientation. So it's very challenging. I think, yeah, the data do matter, and even our earlier work on instance discrimination to discover the objects, we are trained on ImageNet, and ImageNet is object-centric images. If you use other, videos, they correlate with each other, they don't work well. So that has nothing to do with another thing to do with active vision. The oculomotor control, you tend to latch onto the objects of interest. I'll get to this at the end. Okay, second thing I want to talk about is my critique on undifferentiated learning. I think not all the tasks are at equal footing. They are not created equal. And I want to say that segmentation should never be formulated a problem on its own. It's not an end task. I think the way Sam is formulated is just simply the wrong approach. Okay, I think segmentation, what I'm demonstrating, segmentation should serve the master for recognition. So given set of images, can I, only at image level supervision, can I figure out the decomposition of part and whole? So when we work on unsupervised segmentation, I'm asking the question, can semantics be learned from nothing but data? And the image, and in MM's COCO, it's segmented, colored in such a manner. And if this, this is like hypothetical passing tree, maybe on the top level, you want to figure out the scene type, it's outdoor scene. And then you have figure in the ground. Figure is made of people with this red color indicating people of interest, and the ground may be curb, or the grass, the rocks, so on and so forth, okay? Same image in dense pose, you are picking different nodes of interest. You don't care about all the differentiation in rocks, curves, and so on and so forth. It's all just background, but you care about the human body decomposition into 14 body parts. So the question is, you see, in segmentation, usually supervised learning, and there the vocabulary is given to you, and there the examples of annotation are provided for you. If we do unsupervised segmentation, how do we, if we ever learn something, how do we convince the rest of the world we are learning something useful? Which granularity are we aiming for? If like every annotation scheme is picking the nodes on this passing tree, which one should we aim for? This problem is thrown at us. We have to address this. Otherwise, how do we benchmark, right? How do we demonstrate we are learning something useful? For example, so this asks the question, right? We don't have any labels or text. What do you see in this image? What does scene mean to you? Can we define it within the scene modality? Do we not see if we have no words for what we see? Okay. For this image, if you don't see anything, clap your hands. Maybe you can treat this as a bunch of ink blocks. Nobody? Okay. Okay, let's say so. Actually, I've done this a few times. So actually, there are quite a few people don't see anything. I tweak the famous illusion. Okay. If you see a girl, clap your hands. Okay. If you see a woman, clap your hands. Okay. A lot fewer people see this as woman, but I tweak rotate the perspective to show that what woman would look like. Okay. Same image, you can see different things, okay? You need 3 models for recognition. For segmentation, you can look at a figure ground, and they will have different segmentation masks. You can look at the different granularities. You have yet another set of solution. You need 9 models to model the segmentation and recognition. And my view is that segmentation and recognition, they are just a continuum of the passing hierarchy. And one kind of segmentation goes with one kind of recognition. They have to happen at exactly the same time. You cannot have a woman's passing and yet a girl's recognition. This never happens. They have to be consistent. Okay. So here's my answer. I ask, what do you mean by seeing? What does it mean by seeing? Okay. My answer is that given an image, I have a way to group them differently. Initially, all the sensors are recording the light. When you don't see the grouping, you are passive. You haven't seen, you are not seeing anything. But once I see, the blocks, and I group in a certain way, I'm seeing this ink group. I don't need a label for it. If I see the organization, I see this. You can give a different name, but this is what I see. Likewise for girl, you don't need a girl label. Okay, this is the seeing to the first order approximation. First order business in seeing is to see the grouping. The grouping is not random. There's internal consistency. Okay, that's my answer. I'm going to take it to my modeling. Given the image, the prior work, if with all the tokenization, this text-inspired VIT, you have patches, and for classification, you use labeled images as supervision to train a classifier. You use pixel-wise labels to train for semantic segmentation. And you use boundary annotated images to train your boundary segmenter like Sam. Okay? For us, we have the superpixel inspired. It's really vision inspired. These are the units of vision. And we have the internal segmentation. We enforce consistency, okay? But we don't have supervision on that. And then we have image level supervision. So this is we take a VIT. The only two things is, one is we use superpixel, okay? The second thing is we have the graph pooling to ensure the consistency. And if our recognition objective could be, if there are no labels, we just do instance-wise discrimination. If there are labels, we use the image level supervision, okay? So we learn something, we do the benchmarking on the so-called PAR ImageNet by Alan Yu's group. They annotated at the object level, you have these categories, you have part level annotations. I want to show you, it's very challenging. You know, the dog is all homogeneous fur, and you want to decompose into the head, torso, legs, and so forth. And you can see that we beat SAM on object level by 8%. To remind you, SAM is trained on 1 billion masks on 11 million high resolution images. And our method is trained on unlabeled 1.3 million ImageNet images, okay? And I want to show you one example. Here's an image. Here's SAM-H, the largest model you can find on their website. The segmentation is perfect. You couldn't ask for more. But if you, because SAM only tells you the boundary, it doesn't give you semantics. We use the same name the segment, given the vocabulary by the part ImageNet. And if you at the image level, it will still consider these as a fish, even though the segmentation is perfect. And on the part level, of course, it also loses it. And the VIT baseline, if it's unlabeled training, you cannot get anything out of it. And our thing has this consistency, internal consistency enforced. And we get a fish, we also get a sense of the head, body, and the fin, okay? Then I want to take a swipe at this philosophy. You know, if it's object-centric, right? For example, the fish, if I can prune the background for you, of course, the recognition is perfect. But what about this fish occluding the person? You get a perfect human body, right? The top and bottom part. But when you name it, actually still considers fish. You have an outline of fish. You never seen this in the training set, and you will get the fish instead of human. And this is so interesting. What do you see in this? This is called. What do you see in this image? Do you recognize anything?
A
lot of bees, okay? You see the black ink in front of the bees, they don't add anything to bees, right? So if I take away the ink, now the bees are not so recognizable. It has the same idea, right? People always want to segment it. Everything belongs to the object and it should facilitate recognition. No, actually occlusion could help you as well. You see much better when there's the facility group, it facilitates seeing. Okay, so we have this model, you give an image, let's say we train with dog versus non-dog. This image is complicated. It has a car, it has two people, then there's a dog. But I'm only interested in dog versus non-dog. So if you run this, feed forward for a trained model, the dog, it's 54% versus 46% non-dog. It's a winner, it's a weak winner. So your vision system say, I think I see a dog. And then you work it hard. Let's try validate that. You're working harder. So computationally, I want to maximize the response. And then I backprog, modify the weights. So the first one is a vision at a glance, first glance, right? You have 54% of dog in the thing. When you modify the weights, and once the weights are modified, you feed forward again, you pass the image through this again. That reflects vision with the scrutiny. You have a purpose. You want to increase your detection of the dog. And now the dog fires at 97%. But look at the segmentation. We never have segmentation labels from only the top partial back of the dog in the first row, and the last row, the third row, you can see the whole dog gets segmented. Again, I want to say that the concurrency, the consistency between segmentation and recognition, they always go in hand, not only in the first glance analysis, but also in dynamic updates. Okay, we extended this problem to hierarchical semantic segmentation. Hierarchy is a very much overloaded term. You know, saying you can an image you classify as a dog, you can classify as a groundhog. That only plays in the semantic space, right? You refer to the same entity, okay? But we are modeling this problem. The problem with that is that if you have a hierarchical classification, at the top level, you just want to say birds or plants. And the next level, you know, the birds are, you know, going into finer grained birds. Plants are finer grained plants. If you look at the classification at each level, they really look for different things. And you can see that if you look at once it's trained, coarse grained and fine grained, they discover different visual evidence to support them. But in reality, if I want to have a hierarchical semantic segmentation, I want the thing to focus on the same thing. Okay, it could be the bird itself, could be the beak of the bird for finer grain, but it has to be part of the bird, right? So all the prior work, they only impose laws in the semantic space. Our work extend the previous, the one I just introduced, to hierarchical segmentation by simply asking at a coarse grain level, you go for coarse grained semantic segmentation. At the fine grained class nodes, class token, you impose fine grained classification. But in a way, I'm transfer the problem to the different levels of grounding. They are differently visual grounded, but the visual parsing itself has a guaranteed consistency. So I use the internal consistency in grouping to derive consistent hierarchical semantic semantic classification. And you can see that we compare clip. You know, you can give different vocabulary for coarse and fine grained. The blue ones are clip, the orange ones are bar. The first one is every level is correct, the green nodes in this tree. And you can see our bar is much higher. You want everything as fall in that bin. The rest is like you have coarse right, fine wrong, or coarse wrong and fine correct. And this last one is all around. You want to minimize the bar. You can see our bars are lower in every category, okay? This shows foundation models are poor at hierarchical semantic segmentation. Internally consistent segmentation helps hierarchical semantic segmentation. And in turn, semantic hierarchy also helps unsupervised segmentation. Compared to our earlier work looking at the flat organization, the caste work, you can see that our hierarchical caste, H caste, you can see that, you know, this is a completely color-coded. This is the one level, and that next level, we are only varying the hue. So if the blue this is a refinement of that, and this we are varying the value. So the color matches to indicate the hierarchy. You can see that we can figure out the fish much better. You know, this internal consistency really popping out the structure without any supervision. Okay, so that's the second work. Do we have questions?
So I want to ask how we get the superpixel segmentation.
Off the shelf, many superpixel. So of course, like for example, the pole, the lamppost, very thin structure. Something the contrast missing, you may get it wrong. It's very hard to correct. What we are working on is to go feedback all the way to the first level. Superpixel is nothing that more than just a you can think of attention map over pixels. So that's doable. We just yeah.
Can we use
Have a-
SAM mask as a kind of superpixels?
Use what?
The mask from SAM.
Oh, that defeats the purpose. My goal is to beat Sam. I don't want any supervision.
Okay.
Okay. Okay, the third work I'm going to talk about is when you think about categorization, most time you're thinking about this concept, the coin in cognitive science. We are talking about basic level categorization. Things you interact, right? In the land, on the land living, you have pets on the farm, you see, you know, dogs, you know, cats, so on and so forth. But there's also a concept in cognitive science called ad hoc categories, okay? Basic level categories, usually you have this very nice visual similarity You have this, in the memory, it's much better established, okay, just because of ecological exposure. And then there's a thing called things you can sell at a garage sale. You know, see, this is a, you know, there you have a lot of intrinsic similarity. Here, you don't have that, right? And ad hoc categories are created to accomplish certain tasks. It's on-demand categorization, okay? And so we study this open ad hoc categorization. The setting is usually like this, things for sale. If I ask you to do exhaustive search, you cannot give me a vocabulary ahead of time. I can ask you to verify, right? So usually, let's say here, you pick out, say, boots, the old boots, shoes, and old toys, okay? You have few labeled examples with the name, with the instance. And then with that, your goal is to, you know, figure out anything else that also fit that description. Let's say this is unknown knowns. You haven't labeled them. You want to use the label instance to label the unknown ones. Okay, unknown knowns. Yeah, and you can find the boots, shoes. Okay, and then the thing is you want to deal with unknown unknowns, right? Hats. Old hats probably can also be sold at a garage sale. In order to accomplish this, you can think of it has to go from visual similarity. You have to build on top both visual similarity and a semantic correlation, right? You need to rely on both. And this problem can also see in the computer vision benchmark, the Stanford data set. Same image, you can look at it differently. If you're in robotics, you want to figure, you know, what actions, okay? If you're doing the localization, you want to look at whether it's indoor, whether it's a natural environment or residential home, for example. So this ad hoc category is providing you the context, okay? And you have partial vocabulary, you have walking and running. And then there's a jogging, you never have examples, or you never have vocabulary, you need to fill in the blanks in the vocabulary space. And you have sparsely annotated data, okay? So that's a problem setting. And if you embed the given vocabulary on using CLIP, this is like the basic level organization you could have. It's statistical, you can see that, you know, even they sort of cluster differently, and each image they all have 3 labels on action, mood, and location. But the image cannot be everywhere in this image plane, okay? So our goal is to say, you have this partially sparsely annotated data set, and if you go for the fixed text encoder and image encoder, they don't form cluster. It doesn't help you to discover the categorization. We are gonna use, we are gonna train this context, global context token. We are gonna modulate the feature so that they form nice clusters according to the context, okay? And on this data set, you can see we are way better, especially on the novel concept discovery. And overall, like you can get all categories, all contexts right, action, location. We are way better than things that based on words or semantics or based on the visual similarity. And this is to show, you know, this is original CLIP feature. Once we modulate with context, so much better cluster. Those that doesn't have the stars that we never have labels for, yeah, they form a cluster and they extend accordingly, according to the context. This is for action. Okay, yes.
Yeah, I just have a question about the method.
Yeah.
So, do you start with the basic clip model, and then do you put another like a different loss and fine tune, or like what is? I didn't fully understand the method.
Correct. We freeze. The encoder for text and image we freeze.
Okay.
We only train one global token. So if it's action, we are going to learn this. If it's a location, we're going to learn this. If this action, then the global token is going to modulate all the features derived from individual images. So it's contextualized feature. But it's only one token though.
Okay.
It's a global token.
Right.
And then they should form good cluster on the label data and unlabeled data. They should form good cluster in the visual space as well as the text space.
So just to clarify, now each image has 3 embeddings, right? Because you put 3 different.
Correct. So I'm showing you one, but you can see for mood, there'll be another feature. This feature is always same, the statistical, like a general feature representation. Once I put a context in, the feature gonna reorganize according to this. Okay, beautiful question. And this is, if I look at the saliency, right? Between baseline and this three different contexts, you can see that for action, we are looking at the hand. For the location, it's everywhere in the image. For the mood, it tend to look at the face, so on and so forth. And it's very nice result. You can see here, fixing a bike, right? It's focusing on the baseline will be focusing on the bike, not on the fixing aspect. And transportation, city streets, so on. So you can see, I thought this is a very nice about this grounding through, through this contextualized feature learning. Okay. So I started by criticizing this multi-faceted inverse learning, undifferentiated, and what's my proposal? My proposal is segmentation occupy this center space. And, all the other things, it supports all these different tasks of interest. And what I want to take to the next is I want to do unscripted, action-grounded visual learning. And if I have a few minutes, I want to show you something. We are going in that direction. I want to show you some work in progress just submitted. Just rebutted. I want to show that octopus is my muse. Okay, I like octopus because they have the soft tentacles and all the rigid RGBD sensor won't work. Right? They are more formable. They can do the camouflage. They don't need to see the color to be the color. They are intelligent, even in a solo. It's a solo animal, a solitary animal, and they're adaptive and playful. Resilient. Okay, and J.J. Gibson's said on natural vision. How do we interact with the world? We look around, walk up to something interesting, and move around it, so as to see it from all sides, to go from one vista to another. Okay, and we talk about invariance, recognition. Invariance is so important. If you change your view, you don't recognize anymore. That doesn't help you to survive in the environment, right? And there are all these different kinds, day and night, environmental change, and illumination change, viewpoint change. We need to have the invariance for embodied agents. But the thing is, there are many different approaches to it. People play with data models, feature extraction. But in human vision, the invariance is partial. You don't have full invariance. The flower, it doesn't matter, you spin it all around, you still recognize the flower. But 6 and 9, you can't spin arbitrarily anymore. And it's task dependent. If there's only 6, no 9, you can spin it all around. And see this, these two images are identical. You just, turn it other way. You don't recognize anymore, right? It's pose dependent, right? It's okay. And big data, big model, big supervision are not the answer to achieve invariant recognition. Just to show you the clip, slight change in viewpoint, it will go from drum set to dining table. A SAM, the segmentation, if you turn the image, it will not get the same results. In human vision, there's this thing called a mental rotation. How many of you have heard of it? Okay, few. But okay, so the idea is that, you ask people to study, okay? Usually the rotation in depth is more challenging, okay? And the time it takes people to recognize it coincides with how much deviation there is in rotation depth. The bigger change, the bigger time, as if mentally you're rotating the object to the configuration you're familiar with, and then recognize, as if you're performing some canonicalization. So our idea is that don't try to build an invariant recognition engine. That's neither useful nor it's a moot point. Okay. Our idea is to search over transformations at the runtime. You learn recognition engine on natural data. You not trying to, because it's acquired, it's data driven. You just learn whatever the best you can do on the data you have. But at the inference time, you search possible transformers, you find the most likely one. So for example, this color, you treat it with a color, and then you can figure out what is most likely one. And with the foundation models, it helps you. Stable diffusion give you a sense of the likelihood, how one image is more likely. And the classified energy is how well I can recognize this image. We do the energy, combine these two energy terms. You can see that the good thing is stable diffusion is a general natural distribution. If I'm interested in color, I can just slice the distribution along the color transform only. And I have the clipper recognition, this for the conditional recognition, and then the standard diffusion for likelihood. I add them together and find the best one. I can do the recognition. So we are working on this invariance, not by working on the components. The invariance emerges from interaction among non-invariant components. And this method, because we build on top of foundation models, it works across data sets, transformation tasks, and no training is involved. So we can do color shifts, we can do 2D rotations, improve the performance, and we can do 3 viewpoint change of an object verse. And you can see, especially from the worst view, we can give much better, much significant boost. And for day and night, we can automatically turn night scene into a typical information-rich day scene. Okay, and you can think of you have a nerve model. If you have a internal the eye of the mind, you can figure out, you can have initial look, but if you have certain concepts or objects, you can latch onto the one. After your optimization, you latch onto the one that corresponds to an object. Okay, the optimized version. If the random view, it will be some random scene. That's kind of like the foveation, the one the first question about, can you learn something useful from a random videos? And then the question is, we have another earlier work, talk about, can I learn task-driven invariance? So here we actually not only learn the distribution with the normalizing flows. It's instance level. I know how much invariance per instance has. You can see that the different 6 and 9, you can see the rotation invariance in the class. Okay, I'm getting to the end. So the last thing I want to talk about is we have some robotics work. You can see the impressive videos from UC Berkeley, from Xiaolong's group at UCSD, all very impressive, but they are focusing on the motor primitives. There's an experimenter pointing the direction, and they never interact with anybody. On the other hand, high end, you have navigation. Here you can see there's no cluster. You always figure out the plan. I think this is the wrong approach. You are studying these skills at the two very ends. And I think this need to come together to integrative skill development. So we learn both locomotion skills and the navigation skill in one. And that's the end. Sorry for running over time. Okay. Yeah.
All right, I know people have to leave because we're a little bit over time, but if people have questions, feel free to stay and ask questions.
I guess so. In the last work that you were presenting, the idea is like we have these known transformations that we can search in the space of. I wonder if there's any work on like finding new invariances that could exist, and then being able to search in those spaces like that aren't just predetermined.
So the few some of the examples we don't even know, like the day and the night. It's very complicated, right?
Mm-hmm.
We just look at the feature in the corresponding to the two images. We are evaluating along the line, in the latent space. We find which one will correspond to the most informative one, and we show that it picks day overnight 90% of the time. So that's like complicated. You can't say it's a rotation, 2D, 3D, or color.
So it's like in a learned latent space.
Yeah, it's in the same thing with this. Yeah.
Thank you for the nice one. So I also have a follow-up question. So is the transformer a mixture of multiple transformers, or do you assume?
Right now, some 2D is, we just studied 2D rotation. 3D, we use 0, 1, 2, 3, 3D viewpoint change.
Okay.
Color, we just look at the color shift. So these two examples, like it's more general.
I see.
Yeah, we don't have any, yeah, we can evaluate them.
Yeah.
But we actually don't have any parametric transforms.
I see, because if I remember, like, for like training, like these supervised training, there are like these like very complicated randomized augmentation technique, right?
Yeah, yeah.
So if we can do the reverse, basically, like, let's imagine we have a set of multiple transforms.
Yeah, yeah.
Can we learn such like optimality of these combination of transforms? Like,
Yeah. I know what you mean, but I'm trying to make it more flexible.
I see.
Because invariance is partial and acquired, you don't want a full invariance. You really want the data driven. So I want this to be, this is captured by the natural data distribution.
I see.
Yeah. So I want to relax the type of transformation I'm looking at. I want to relax the kinds. But if you restrict it to like color correction, I'm slicing the distribution in a particular way.
Mhm. Yeah, that makes sense. Okay.
Okay. Great. Thank you so much.